I am in a black hole hunt, and let me show you what I've actually got so far. I was trying to write, I thought I would do this a week ago. I was trying to just write up the black hole discussions that we'd done on the live stream. And I discovered that it was more complicated than I thought. Okay, so let me show you what I figured out and what I haven't figured out. So, blah, blah, blah. Okay, so here's a causal graph, and this is a pretty decent cosmological event horizon. And okay, that's a fully disconnected horizon. Okay, this is a universe stops, but it stops in two places. Okay, makes sense?
Yeah.
Okay. So then I'm talking about black hole-like event horizons, which are kind of one-way event horizons, where you can go from one equivalence class of states to another, but not back. Make sense?
Right.
I mean, this is a very trivial one. Okay, so now we've got a less trivial one here, where we go from this side to this, but we're not able to, where some things populate just that side, some do the whole thing. Okay, so far so good. All right, so now I wanted to go sock hunting, okay? And by a sock, I mean one of these dead ends. And I'm trying to understand both. Okay, so I did a search, and I haven't looked at some of these yet, but I did a search before. Let's see, this is all, okay, so I wrote some code that is, where is it? That is simply decorating causal graphs, and it's asking if you go one additional step in the causal graph, do you have an end that doesn't expand on the next step? Am I making sense?
Yeah.
Jonathan, are you with me?
Yeah, of course. Yep.
Okay. So
which will not in general be a normal form.
That is correct. It's a partial normal form.
Right. Normal forms will be dead ends, but not dead ends are not necessarily normal forms.
That's correct, because here, this is just part of the causal graph that dead ends, right? Is that the point you're making, or are you making a different point?
No, I'm making the trivial point that yeah, this is these are a more general case that yeah, as I say, these are a sufficient but not necessary condition for a normal form.
Well, first they're part of the graph, and the second thing, they might be used in another event after arbitrary many number of steps.
That's true. That's true. So you don't know they're going to be until the whole thing stopped. You know, things are not over until everything stops.
Right. Well, space-like singularities can't be defined without reference to future null infinity.
Right.
But I was just making the point that obviously, as I say, normal forms will be instances of these, but not vice versa.
Well, like that case that I was showing, because the normal form is everything ends in a dead end, correct?
No, it's just that no, that's not correct. It's just that if an event that yields a normal form by definition cannot be causally connected to an event in the future.
For sure, but you're saying, so let me make some notes here. You're making the point.
I'm not saying anything sophisticated. This is all stuff we already knew.
Yeah. Okay. Fine. But I'm just gonna make some notes about dead ends. Okay.
So it's a local, potentially temporary dead normal forms.
Well, I understand it might be temporary, right? So,
but actually, but there are cases where it's not even a temporary normal form; it's just something else, right? Where the event acts on. If you mean local in space, not in space-time, then I agree. If the event acts on a spatial region that it then just isn't causally used in future events, then it's definitely not a normal form, but you can think of it as a spatially local normal form.
Sure. Because that event, right, you're just saying that is a, what on earth is going on here? Don't crash on me. Come on, you stupid creature. Oh, for God's sake. Okay, finally. What is that? Okay. What is going on here? It did take a while. It took a couple of hours to do one of these, because I did a full search of all, what was it? 2, 2 goes to 2, 3. No, 2, 2, 2 goes to 2, 4. All 40,000 of those. I found all the cases of this. Okay. So first statement is a global normal form. Something could be a global normal form. Let's see, that's the whole universe stops, right? I mean, in these pictures, this is a single, yeah, that represents the whole universe stops. And another thing is a local normal form. A piece of the universe stops. Hey, actually, I wanted to mention something. Hold on a second. Okay. Anyway.
By the way, at some point, I'm a little bit confused about your second incompleteness theorem thing. I need to talk to you about that at some point.
Oh, I'm totally confused too. I mean, I think that
because to the extent that I understand the claim, I think it's kind of obvious. So I need to understand which part is not obvious.
Okay, so here's the part that's not obvious, okay, in my view, and I don't have it quite. Okay, why does the universe exist?
Yeah.
Right? Okay, explain why does there exist a... Wow, have you guys been editing that?
No.
Okay. Why does there exist a, a number such that blah, 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 right? Mm. Okay, so the answer to that will be a proof.
Yeah.
Right? And that proof is a mathematical statement, quoted in terms of certain primitives.
Right, some object language.
What's that? Some...
Well, like, you know, the Ross's object language for formalizing the second incompleteness theorem.
Above my reading level, I don't know that.
That's the object language resolves the philosophical problem of what's the formal system you use to prove the incompleteness theorems.
Okay, well, that's
and is that language itself subject to the incompleteness theorems? But anyway, sorry, that's a...
Okay, but anyway, so then the question is, can you... The question, why does the universe exist, becomes a proof. And its
answer becomes a proof.
Yes, its answer is a proof, right?
Yeah.
So then the question is, what Gödel was doing was to show that proof, that statement about proof, could be compiled into arithmetic.
Of course, yeah.
So the goal here would be to show, can you compile the question, the statement, can you compile the proof of why the universe exists into something which can be represented in the universe?
Yeah.
And then...
yeah, okay, sorry, go on.
Is this obvious to you?
I thought so. I mean, so the first incompleteness theorem in the case of, the first incompleteness theorem, you can formalize it in terms of a diagonalization argument.
Indeed.
Right? And you can make the analog of the first incompleteness theorem in physics is the computational irreducibility of the laws of physics.
Yes.
Because what you do is you say, suppose we could build, suppose that there exists an algorithm for physics, P. Suppose we could build a computer that ran P, that simulated P faster than P itself evolves, right? So then you could make predictions about the outcome of that computation in such a way as to contradict the algorithm.
Yep.
So you get the first incompleteness theorem. So then the second incompleteness theorem, one way you can formalize its proof in the pure logic case is you say a proof of omega consistency in Peano arithmetic to prove the consistency of Peano arithmetic effectively involves showing that, that there's no contradiction, and in particular would require some procedure for enumerating all semantically true propositions in Peano arithmetic and showing that there were no contradictions. But the first incompleteness theorem tells you that there is no such mechanical procedure for doing that. And so all you have to do is say, I think for the physics case, is to say, basically, your answer to the question of why does the universe exist has to take the form of some theorem that says, if X is true, then the universe exists. But the universe, as long as existence is a non-trivial semantic property, then to say the universe exists also requires saying that all of the systems within the universe exist, and therefore, say as long as existence is a non-trivial property, would require explicitly simulating all systems in the universe to show that they all exhibit the property of existence subject to the hypothesis X. But our analog of the first incompleteness theorem tells us that no such procedure can exist.
I think if there is a semantics for existence, I think that's where things fall down. I think that's where the Anselm argument falls down. I think that's where the Gödel argument falls down. I think that's the part that's not so obvious.
Oh no, I know, absolutely. I agree. The question of is existence a predicate? That's the thing that I know.
I know, but so
people have been arguing about for ages.
Right. So we have to operationalize that in some way, and that's what the question of whether your claim is if existence is a predicate. Anyway, we should take this. We should do a live stream about this. People would enjoy this.
Crucially, if it's a predicate and it's a predicate that requires a non-zero amount of computational effort to determine, then I think we can prove it requires an infinite computational effort to determine for the case of our universe. And therefore, a statement of the form X implies our universe exists must be undecidable for all computational systems that exist within the universe.
Why do you think that if it requires, wait a minute, if the existence of X, you're claiming that it somehow has to entail the whole, to show that the universe with all its subsystems exists, is something which effectively requires, because you're saying, well, this small part of the universe could exist, but for the whole universe to exist, you have to somehow be able to show existence for all of those subparts.
Well, okay, let's take the mathematical logic case, right? So the way, the way that at least the version of the second incompleteness theorem proof that I know, which is the Rosser one, the way that essentially works is, you say, ultimately we have to, if we want to prove omega consistency, we have to enumerate all semantically true propositions to show that there's no contradiction, because, otherwise you could just show me some system and say, oh, it's omega consistent, but then I don't know whether it's equivalent to Peano arithmetic or not. To know that it's equivalent to Peano arithmetic, I basically have to know all of its semantically true propositions, because that's the actual content of it, and I have to check whether those are the same as the true propositions in Peano arithmetic, and I have to check that they are themselves consistent, and then it's in doing that you get bitten by the first incompleteness theorem that says that there isn't a procedure that allows you to do that. My claim is the same thing is happening here. Suppose you say the universe exists, and I ask you to try and convince me that it does. You show me some system and you say this is the universe. The only systematic way to convince me of that, I claim, is to show that all of the subsystems that it entails are the same as the subsystems that our universe entails, including, in particular, the analog of Gödel sentences, which are universal computers.
So you're saying prove the thing exists requires proving the existence of the prover, so to speak.
Amongst other things, yes.
So you're saying that to prove that the prover who is in the universe exists, you must basically show, but it's a little different than the question I asked, which is why does the universe exist? Not does the universe exist?
No, but my point is that if you're trying to determine, so suppose you gave me an answer to why does the universe exist?
Yeah.
ultimately, I think it would have to take the form of some logical statement like X implies the universe exists.
Sure.
So how do I go about proving that? Well, I have to assume X is true and then deduce that the universe exists. Okay, how do I go about deducing the universe exists? I suppose I deduce that something exists, Y exists. How do I determine that Y is the universe? Well, ultimately, I have to enumerate, I have to do some procedure that is equivalent to enumerating all of the subsystems implied by Y and comparing them to the subsystems that are known to exist in our universe.
I understand.
And in
it's an
particular,
interesting topic. I think there's more to say about it. I think this question about existence as a predicate is something that I bet we're going to have something to say about, even though that's been a flapping around question for a long time.
Right. I mean, yeah, as you say, that's the main sort of theological objection to the ontological argument.
But I do think it necessarily has to be an if statement.
What do you mean?
Well, whether you're trying to prove that universe exists from something else, but if you have laws of physics that don't necessarily exist because of something else.
No, but the thing is, the question is, why is the universe actualized? And
which is not quite the same as the question why certain number exists, because why certain number exists is essentially a question of whether it's possible or not, or consistent.
Yeah, I know. I don't think that why does the universe exist? I don't think we know. Yes, I agree with that. And I think existence, we need to find a way to make a meta-ontological statement, basically. That's what we're trying to do, is we're trying to do meta-ontology. We're trying to do ontology, we're trying to do the meta-mathematics, the analog of what we are trying to do is to ontology as meta-mathematics is to mathematics. Anyway, let's go back to the much more concrete story of black holes for a minute, especially since I gather Max has to go soon.
Yeah, in half an hour.
Okay. But yes, isn't it a lovely topic, Jonathan, even though you think it's trivial?
No, I need to understand where the depth comes from, because I think we can. I think we can make basically, as long as we assume certain properties of existence, which I agree may or may not actually be true, I think we can prove fairly straightforwardly an analog of the second incompleteness theorem.
Yes, I agree with that.
But I need to figure out where to go next, and that's
I agree with that. But I think the depth comes in making a meta-ontology.
Sure.
In other words, I think what Gödel, the whole idea of mathematicizing meta-mathematics was the key idea that Gödel had.
Right. We need a Gödel numbering for ontology.
Exactly. We need a way to meta-ize ontology. That is a way to talk about, there's a way through this. I think there's a way through it. And I think the end result will be a proof along essentially the lines you say, that for an entity that to explain why the prover exists, the prover cannot explain why the prover exists, more or less.
Right.
And, but I think there's a little bit more to it. I think there's a need to define a meta-ontology as Gödel defined,
one nice feature of that is that it would imply that there's an infinite hierarchy of universe ontologies, where it's like, universe,
like the arithmetic hierarchy.
Exactly. Yeah. Universe plus the axiom that the observer exists, plus the axiom that the observer of the observer exists, etc.
Mm-hmm. Yep. While we're at it, why don't we solve a multi-thousand-year problem of philosophy? By the way, let me just make one more comment here. Anyway, so, all right, let's look at dead ends, okay? So, a local normal form is a piece of the universe stops. That's like a space-like singularity. Do you agree?
Yep.
So, I've been on a hunt for pieces that stop. Actually, another thing, okay. So it could restart after an arbitrarily long time. When do I know that it couldn't restart? I mean, there are ones with strings where we know it can't restart.
Well, depending on the rule, it might be easy to see. Like if you produce 3 edges and no 3 edges in the inputs.
Sure.
But I suspect in general it's an undecidable question.
Of course. Okay. So, all right. That's my dead end hunt. Now, let's talk about the singularity theorems and naked singularities and things. Okay. So I can find pretty good, okay. So the problem is there are very few trapped surfaces around the dead ends. Would you expect trapped surfaces around the dead ends? I mean, it's surprising me that very few of them have trapped surfaces. In fact, I haven't found a single one that does yet.
Yeah, which is interesting. And I'm trying to get a sense. I don't have good intuition for whether or not that's surprising. Because what I'm trying to get a sense of is scale. Because it may, what I'm wondering is, are we seeing that there's a trapped surface, but it's kind of a degenerate case, right? Where it's actually at the point of the singularity.
Well, quite.
And how big a causal graph do you need to create for that not to happen?
Right. Well, okay. So you guys agree, I'm not being stupid. It isn't obvious that there's no trapped surface, right?
That there is or there isn't?
That there isn't. I mean, so in other words, you would expect.
My intuition was that there would be trapped surfaces.
That was mine too.
Yeah.
So in what sense?
Well,
What
it's
is a
like
naked
harder to
singularity?
create.
What?
Because trapped surface means you have a whole subgraph where the rule doesn't apply anywhere. But for a single event, you just need, well, essentially 3 or whatever many outputs for that event. So it just seems less likely that you would get a subgraph, which is large.
What are you saying? I mean, you're saying that there could be a
So for trapped
subgraph.
surface, you need an entire subgraph where the rule doesn't march anywhere. But for a single trapped event, you just need its outputs to not match to anything, which seems to be much easier to produce.
I don't understand.
Why does a trapped surface need the rule not to match a subgraph?
It just has to lead to something which doesn't match.
It means you have a bunch of events, outputs from neither of them match to anything. That would be a trapped surface.
Well, no, they only match to things on the interior.
I'm going to go do more of a hunt. I'm going to hunt in some substitutions.
Are we using the phrase trapped? I'm confused. Are we using the phrase trapped surface in the same sense? I'm using it in the sense of GR, of causal edges point towards an interior.
Right. So in other words,
Max, are you using it to mean a spatially extended normal form?
Yes, I was.
Okay, that's not the sense in which I was using it. Okay. I don't think that was the sense.
Yeah, in which sense did you use it?
Well, okay, so you're saying, okay, so these are spatially extended normal forms.
Okay, so Max, you're just talking about a collection of dead ends in the causal graph as opposed to a single dead end.
Right.
Yeah, but that's just that's a spatially extended singularity case, right? That's not a trapped surface.
Right.
Okay, so let me ask you another question. So, okay, so we've got, in a naked singularity scenario, what do we think of physical naked singularity? A naked space-like singularity, do those occur in general relativity?
They shouldn't do.
Why not?
Because of weak cosmic censorship.
I understand that. What's the difference in weak and strong cosmic censorship?
So it's kind of confusing. I mean, they're related very broadly, but strong cosmic censorship really doesn't have anything to do with black holes. Strong cosmic censorship is basically the statement that GR is deterministic, that you can define sort of C1 future extendability for the Einstein equations. Weak cosmic censorship is the case about naked singularities. They're related in a sense.
This is hyperbolicity in a sense. Strong cosmic censorship.
Sort of. It's a bit more subtle than that, but basically yes. It's strong cosmic censorship is a statement about the Einstein equations in bulk, so to speak. Weak cosmic censorship is the statement about naked singularities. But it's kind of I think it's really silly that they're called weak and strong, because there exist spacetimes that violate the weak cosmic censorship and not the strong one, and vice versa. So neither is strictly stronger than the other.
Okay. Okay. So no naked singularity without a trapped surface.
Exactly. But the reason why, okay, so earlier when I was saying it might just be that I think the causal graphs aren't big enough, is, the reason we expect there to be a trapped surface is for gravitational, due to gravitational effects. And we just don't really know how big the causal graph has to be in order for those to become relevant.
Yeah, I know.
So I'm not, it doesn't concern me hugely. It's a bit intuition breaking, but it doesn't concern me hugely.
Well, okay, fine. But I mean, we can go on a hunt. We will hunt. Okay. But I'm trying to understand physically, how does a naked singularity ever, I mean, I'm confused about the fact that nobody ever knows about the naked singularity if it only affects events that are right next to it. See what I'm saying?
Right.
I mean, what does it mean if there isn't a trapped surface? What does it even mean to have, okay, so a singularity is something where things just stop. But if there was a trapped surface, there'd be a whole, essentially past light cone of the stopping point. That would be its catchment area, right?
Sure.
Now, I mean, what we're effectively saying is, the past light cone of a dead end tends to be trivial, right? What would it look like if it was a naked singularity that was out in the open, playing its pawn, so to speak, or whatever?
You mean what would the past light cone look like?
Yeah, isn't the past light cone just the trapped surface of the singularity? In other words, if there is a past light cone, a non-trivial past light cone, we would just say, well, that's the trapped surface. The exterior of that light cone defines the trapped surface of this singularity.
Sorry, I'm slightly confused about. So we're still talking about the trapped, the non-naked case.
Well, okay, so I think one of the questions would be, does the past light cone get to be arbitrarily big?
In which case? I'm sorry, I'm confused now.
In the case where you just have one little dead end, okay? So
does it have an event, or does it have a trapped surface?
What would it look like if it did have a trapped surface? Answer: there would be some subpart of the causal graph that would inexorably lead to the dead end and couldn't get out, right?
Right.
That's what it would mean. That's what it would look like. There would be a past light cone. And so if you go backwards...
Yeah, there would be a region of the causal graph. Yeah, sorry, go on.
No, if you go back far enough, you'll get back to the initial event, and you'll always be able to get back to the initial event.
Yeah, but the point would be that the trapped surface would manifest as, there's a region of the causal graph in which all future light cones lead to the singular, lead to the normal form.
Right. And what we're seeing is...
Right, so the naked singularity case would be the one in which there's, at every point your past light cone could have gone away, but if you make the wrong choice of time-like geodesic, you end up at the singularity. if you see what I mean.
I see what you mean. Let me think about that for a second. So you're saying,
right, the trapped surface acts as a warning, right? Because it's saying, okay, now I'm in a piece of the causal graph and all of my future rays lead to this normal form. I know that I'm going to be killed.
well, the trapped surface is the cusp, so to speak. The event horizon, look, the event horizon, is a cusp on which, go to one side and you're in the, you go to one side and you lead and you go and you're trapped. Go to the other side and you're not. Right?
Right.
Okay, so in the causal graph, what that means is there will be certain poisonous nodes, which if you hit that poisonous node, you're trapped.
Right. Right. It's like,
Okay.
there are nodes where your fate is sealed, independent of your time-like direction. You're going to hit the singularity.
Let me think about that for a second. So you're saying, let's look at a picture here. Let's look here. That node, by the time it went to that node, it's toastified. Right? It's in this trapped area, right? But what we're doing here is it's a node that is trapped. So you're saying from a given node, right, so there's a pre-trapped thing. So before you get to
Well,
a trapped
different
a single
case,
node
because the
could
end
be
is
the
not-
nodes are
interior.
trapped. Nodes can be trapped.
Yeah.
Wait a minute. So you were talking
Obviously, the
on top
interior
each
of a
other.
trapped
Max, what were
surface
you
could
saying?
just consist of a single node. This is not a singularity case.
Well, that's what's happening in a bunch of these things. So you're saying that there is, what's that? Say that again. What? Max, can you repeat, please? No. Okay. Well, anyway, so what you're saying is, if I look at one of these things, which is one of my potential singularity nodes, let's look at this guy here. Okay. Well, we didn't hear what you said. Okay. All right. So let's look at this node here. Okay. This is a very simple case. Right. This node here is, if you get to that node, you're screwed. You're stuck. Right. So this node here still has a choice. Right. See that? So what is the general relativity interpretation of that node there? This is within the trapped surface. That node has both the trapped and untrapped future, right? Jonathan?
Yeah.
Did we lose Jonathan?
I'm
do you agree?
here. I'm talking. Can you hear me? Yes.
No, I can. Yes.
Oh, hang on. For some reason, there's some delay.
So I'm saying this. Hello, can you hear me? Can you hear me? Can you hear me?
I can, but I think there's an audio delay.
Hold on.
Okay, I'm going to leave and come back. Okay. See if it fixes it.
Hello? Can you hear me?
Okay, is there still an audio delay?
Well, I can hear you just fine, but
Well,
you know,
you replied
the
almost
simultaneity
immediately.
stuff has not been defined. Okay, so why don't we use, you know, we can define a frame here, Jonathan.
Mm-hmm.
What?
Right.
Okay. Can you hear me again?
I can hear you.
Okay, fine. So look at this node here, okay? This node has a choice. It either goes splat in there or it doesn't go splat.
Yeah, I understand.
Right.
So this node, the trapped surface is in a sense on that edge.
Well, there is no trapped surface.
What do you mean there is no trapped surface? I mean, there's a trapped surface in the sense that anything in here is trapped. Just isn't very big trapped surface.
What does it mean to be in a causal edge?
Well, you're
saying there a causal edge corresponds to one hyper edge. So if you're
okay.
that hyper edge, you're not going to evolve anymore after one step.
Okay, so hold on. In this case here, do you agree that this corresponds to a trapped surface? The content inside here is inside a trapped surface. Do you agree?
Yes, of course. But the trapped surface is defined at the level of space-time events, not at the level of causal edges.
Well,
right, but you're saying
to one another.
Well, it doesn't really matter. This is a semantic issue. I mean, you're just saying there is a trapped surface, but it's tiny. There's a trap. There's no space between the splat and the trapped surface in this case. Here.
Well, this is a degenerate case in which the trapped surface has zero volume.
Yeah, right. We agree. Right. So the surprise is that we have some socks here. This is a sock. Yeah. My technical term for that kind of dead end. Right.
Yeah, I understand.
This is a sock where, but I have not yet found socks in infinitely growing systems.
Mm-hmm.
Right. So this sock has the property that, I mean, it's always going to crash. It could, a given node could have as its future light cone both socks here. Mm-hmm. Okay, these are nodes that have particular socks as their future light cones.
Right, I understand.
Okay, so now the question is, so what I expected to see was that there are, you know, regions of the causal graph that go into a particular dead end that represent trapped surfaces around particular space-like space-like singularities. Now, a question would be, what is this? This is not a space-like singularity in the same sense. Time does not stop here. What is this?
Well, that's a trapped surface without a singularity.
Do those occur in general relativity?
Yeah, sure.
Example.
Of what?
Trapped surfaces without a singularity.
Well, like around a collapsar or something.
What is a collapsar? I thought a collapsar was a black hole, was another name for a black hole.
I know, but you can have that. There are solutions that involve eternally collapsing stars that don't become. Hang on, maybe I'm using the wrong terminology. I read about these a while ago.
And how does that relate to the Hawking-Penrose singularity theorems?
Oh, so these are a way of getting they effectively violate, or they circumvent certain axioms of the singularity theorems related to Lorentzian extensibility. So you can have eternally collapsing objects that form event horizons but don't form singularities. They're not believed to be physical.
Okay, but so what? Okay, so eternally collapsing, but so what goes wrong? I mean, in other words, do we think this looks like one of those creatures?
No, I don't think so.
So what the heck is this? I mean, this looks like it's a finite dimensional thing. It's not. I mean, the singularity theorems, I gather, are only true in 3+1 dimensions.
Sure.
Are they true in 2 dimensions?
By 2, do you mean 2+1 or 1+1?
Let's say 2+1. 1+1. Sorry, 1+1.
I would doubt it. I would doubt it. Because my memory of these things is that Cauchy problems work quite differently in 1+1 dimensions than in 3+1 dimensions.
Yeah, I bet you're right.
But I can double check that.
Okay, so this is something that doesn't form a singularity, but then, okay, so a space-like singularity, we think, is a thing like this, where time stops, right?
Uh-huh.
Okay, a time-like singularity looks like what in the causal graph?
I mean, is that a rhetorical question?
Well, you could answer it if you want to. You had a definite idea. I mean, I have an idea also, I think.
Yeah, I mean, my view hasn't changed since yesterday. So I'm open to ideas, the new ideas.
Okay. But the concept of a time-like singularity is that you can have multiple, your claim is time-like singularity is a beyond max scan. Right? In other words, where there is more that activity that can happen than can be represented by a max scan. Now, how does that relate to the Cauchy problem?
Wait, that is the notion of violation of global hyperbolicity, but that doesn't have anything to do with time-like singularities, as far as I know.
Okay, so then you have to remind me what your idea of a time-like singularity was.
Just that you have a situation where there are many more events. There are many more. It's like for each A that exists in your state, 5 A's are appearing outside or something. So ultimately you have it on the next level. Your space-like separations totally dominate your time-like separations. Right.
Okay, so you're saying space-like.
If you had some situation where, for instance, if the number of A's grew dramatically, so that you went from having 10 events on layer T to having 1 million events on layer T+1, that's a sort of finite approximation to a time-like singularity.
I think there's going to be a simpler case of that. I mean, so what you're saying here is, you're saying, consider something like this. And I can just do 1A. Why is this like a time-like singularity? I mean, why is it like a time-like singularity? What is the... So if I look at the light cones here, you're saying this light cone will be shattered into a gazillion pieces.
Sort of. I mean, 1 to 3 is not as dramatic as 3 is a very poor approximation to infinity, but you see the point.
Well, let me just understand what infinity will look like, okay? Because I don't think. I mean, the question is, can we get time-like singularities? So you're saying, in this case,
we can get true space-like singularities, and we can get arbitrarily good approximations to time-like singularities.
Okay, let me understand what a time-like singularity is in general relativity. A time-like singularity is something where what happens PDE-wise? What's the simplest PDE in which we can get a time-like singularity? It's something where it is not determined by the initial conditions, right? Where the behavior is not determined by the initial conditions.
Yeah, I mean, it's related to the violation of hyperbolicity problem.
Right, but fundamentally, its behavior does not depend on initial conditions. So another way to say that is many behaviors are all consistent with the initial conditions. Is that right?
Well, it depends what you mean by consistent.
Well, what we're doing is solving an equation.
Yeah.
And the equation is just a constraint.
Mm-hmm.
And what we're saying is the constraint does not determine the the behavior in the case of a time-like singularity?
No, I understand the claim. I'm not convinced it's quite correct. I mean, because it depends on the formulation of the equations.
Okay, can I ask this question? If you reduce the equations dramatically for a Kerr black hole, what is the actual minimal reduced equation that is the time-like singularity? What is the PDE for the time-like singularity?
Let me see if I understand the question.
You know, if it's just y double dot equals blah, 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 what is it? What is the equation? Is there an equation?
Yeah, I'm not convinced I understand the question.
Okay, let me try it again. Okay, because I think this is a meaningful question. Okay. So if I define a hyperbolic differential equation, right? Yep. It is an initial value problem. It is determined by its initial values, like the wave equation. You know the answer based on the initial values of the wave equation.
As long as you have global hyperbolicity.
Well, just the ordinary wave equation on a line, for example.
You can still have, you can set up wave equation problems where you get intersections of characteristics.
How? You mean based on the initial conditions?
Yeah, I think so.
I don't think so. I don't think so. I think that the wave
if you have nonlinear coupled wave equations.
Oh yeah. I didn't say that. I said the ordinary wave equation, right?
Okay.
You're saying right. That's the failure case. But what I'm saying is, okay, what I'm saying is that I think there must exist equations that have the property you're describing where they just split out garbage. Okay?
Yeah.
Because why do they split out garbage? Given a wave equation, it's an initial value problem. You feed in the initial values, it does what it does.
Yeah, I understand. Right? Yeah.
Okay.
And then, but at the point where it becomes ill-posed, then that's no longer the case, right?
That's right. And so what it means to be ill-posed is that that many possible solutions are all consistent with the initial conditions.
Not necessarily.
What else?
That depends on whether you're using, on what form of equations you're using. If you formulate them, it depends on whether you formulate them as in strong derivative form. If you formulate them as weak integral form, suddenly.
So what else can happen when you say they're ill-posed? What else do you mean?
Well, there are ill-posed solutions that can be captured if the equations that are well defined and can be captured if the equations are formulated in weak form, but not in the strong derivative form.
Okay, but fine. But the notion,
which I think is I think that's what happens with shockwaves, right? That was my understanding. That if you just take the derivative form of the equation of the Euler equations or something, then the shockwave, then at the shockwaves the behavior becomes ill-defined. But if you take the integral forms, the shockwaves are perfectly well-defined. Right. This is this whole field of studying weak solutions to PDEs. And it's not the case that a weak solution is just something where anything can happen. Weak solutions have their own sort of analytic properties.
Okay, so a weak solution. All right, you're saying the integral form of the equation might be solvable.
Right. I mean, that's what happens with it's what happens with shocks, I think, but it's certainly what happens with black holes. That's basically how numerical relativity codes work in the black hole case. There's this whole moving puncture idea where you factorize your space-time into this, into the analytical part that contains the singularity and the numerical part that's singularity free. And the analytical part has to be in the weak form to ensure that you can capture the weak solution.
Okay, but coming back to what happens at a time like singularity, okay? Isn't it the case, Okay, at a time like singularity, if I've understood, you simply cannot predict what's going to happen. Is that a true statement about a time like singularity?
Again,
It's my
it depends on
understanding.
what
I mean, I was talking to Jose about this. My understanding is that the universe splits out garbage, undefined garbage.
For some formulations of the equations, yes.
Okay, so hold on. You're saying that there's a meta information about the equations which will cause them to do a definite thing at a time like singularity, as opposed to the equations don't say enough, and so you just say, well, it just splits out garbage.
Right. I mean, okay, so look, one way that you can trivially get a time like singularity, for instance, in a causal graph, would be by having, if you had time-like if you had only time-like edges connecting things on the same layer, right? That's a kind of maximal failure of global hyperbolicity. But it would also correspond to a perfect time-like singularity, because at that point, suddenly your notion of time is kind of meaningless, or it's no longer meaningful to distinguish between time and space.
Okay, right? That makes sense to me. So wait a minute. So the quotes going horizontal version. Okay.
Right.
Okay. So hold on. Let's capture that. So I mean, the basic point is that what the hell is that? That's a thing where on a single, I'm very confused by that. I'm very confused by how that would happen. So you're saying going horizontal, we say.
So in standard GR, I mean, what would happen in this? So you can construct spacetimes that are kind of maximally hyperbolicity violating, in which basically your foliation has the property that all of the space-like hypersurfaces eventually stack up on top of each other, right? So it becomes they all kind of end up infinitely intersecting each other beyond some point, right? There's a point in your Lorentzian manifold where you can no longer extend your universal time function, if that makes sense. Right.
Yeah. Okay. So you're saying going horizontal,
all the space-like hypersurfaces crash into each other, and so that's a maximal failure of global hyperbolicity.
Okay. So that you're saying that what would happen is, oh boy, how does this work?
But so the spewing out garbage thing, I think. Well, I don't know exactly what that's about, but I'm assuming what you're trying to say there is that obviously the equations become ill-posed at that point because of this dramatic failure of hyperbolicity. But that was exactly why I was saying that it suddenly depends on how you formulate the equations, because there are still weak solutions to the EFEs at that point. It's just that they won't be captured in the strong differential form.
Okay, I want to understand this going horizontal thing. Okay, so normally, let's try to construct a graph that has that property. What you're saying is, by the way, how do I test for hyperbolicity? I have a random graph. How do I test it for hyperbolicity? Do you understand my question?
Yeah, I know, I understand, but I can give you a necessary but probably not sufficient condition.
Yeah.
Which is that the number of layers should equal the number of time steps. And most of the time when I've seen hyperbolicity failures, that's the test that has failed.
Okay. Well, time steps as in max scan time steps.
Yes, yeah.
Okay, how can I test that more formally? What is the condition for hyperbolicity?
Well, that it's possible to layer the graph in such a way that all of the time-like edges are pointing monotonically downwards. All the causal edges are pointing monotonically downwards.
Okay, so there exists a layering. There exists a Is Max still with us? Because he might have an idea about this.
Yeah, I'm still here, but probably not for long.
Okay, but do you have an idea about this? How can you tell if there exists a layering of a graph such that all the edges point down? Is there some transitive closure approach to that?
Isn't it if it's just a dog that would always be possible? In other words, if there are no cycles, you can always do it. Most trivially by picking one event at a time and extending your foliation to that event.
Right, but the layering in that case won't correspond to the actual layering of the update generations, or doesn't necessarily.
But so what? I mean, if
well,
there
generations
exists...
are arbitrary.
Okay, so the question is, are cycles the only thing that breaks hypervelocity? That's
no.
Okay, so what's an example of something that... What's an example of something that breaks hypervelocity but does not have cycles?
Well, let me see if I can construct one.
I mean, I don't understand why wouldn't we be able to do max scan? Max scan is just defined as we do as many as possible, but I mean, the whole point is as many as possible.
Yes.
No, but yeah, but the point is, if the max scan leaves certain regions of space untouched, that's a hypervelocity failure. Because that's a part of your space-like hypersurface that hasn't evolved from one step to the next. And so in the continuum case, that's an intersection between hypersurfaces, and therefore an intersection of characteristic lines.
Well, that will almost always happen.
Right. Which is why, I think hypervelocity is a more subtle problem than you're making it sound.
Okay, so hold on. So you're saying...
So we need to have every edge update, but not more than once.
What do you mean every edge update?
Well, so Jonan says we cannot have parts of space which don't update between layers. So that means every edge has to update, but it cannot update more than once, presumably.
What do you mean by every edge has to update? I mean, how do we know? You're saying that on one layer of the causal graph here, that the set of things that are being updated, that, in other words, if we look at all these update events, that together they update everything just once and no more. That's going to be very rare.
Well, it is very rare, but it seems like that's what Jonan is saying.
Well, I'm not talking about edges. I was talking about vertices, but yes. I mean, global hypervelocity is a strong property.
Why would we talk about vertices?
Vertices of the causal graph events.
No, vertices of the spatial hypergraph, because those are the things from which you deduce volumes.
Well, you're saying global hypervelocity.
If there's a region of space that doesn't get updated, then, between two successive generations, then that point in space and its neighbor as the next space-like hypersurface intersect by definition.
Right.
That's a hypervelocity.
Well, all the vertices being updated is a weaker condition.
Right. But it's still a reasonably strong one.
But the point is, in a continuous approximation, which is what we will need here, we might consider multiple layers at a time.
Yeah, sure. I agree that there's subtlety about averagings and smoothings of things, which we don't fully understand.
Okay. What's the statement in relativity about global hypervelocity? Where does it fail?
Well, in exactly that case, where you get intersection of space-like hypersurfaces.
No, I understand. hypervelocity fails, but what are the practical examples of that?
So if you have it happens quite frequently if you have sort of weak momentum constraints. So in particular, you can have initial value problems where your energy norm kind of grows super exponentially, and it's known that in the cases of those classes of solutions violate global hypervelocity. In practical GR, it's usually an indication that your problem is not sufficiently constrained, that something is growing faster than it should do. So like in the ADM formalism, it's usually a sign that the ADM momentum constraint is too weak.
I don't quite get that intuitively. I mean, is there some known solution where the hypervelocity fails?
Well, I mean, the hypervelocity fails for ADM. It's known because the momentum constraint is too weak, and therefore, as I say, you get this. If you perturb the initial condition by some amount, it's known that the energy norm for that initial condition will grow more than exponentially.
Well, you're saying in the ADM formalism, it is straightforward to end up with something which does not show hypervelocity.
Yes, right.
I can see that.
Which is why ADM is unstable.
Okay. In other words, because of numerical instability, or just because the nature of the, you're saying normally you would have your lapse function and your whatever it's called. What was the other one called?
Shift vector.
Shift vector, yes.
Yeah.
And so long as you can move forward with a lapse function, you're in good shape.
Right.
But you're saying that can somehow fail by virtue of sort of a current condition like failure or something else?
It's something a bit more subtle than that. It's that, so yeah, in ADM, you're evolving, there are these, your lapse function translates to this Hamiltonian constraint, this energy constraint. The shift vector translates to these momentum constraints. And the spatial metric for each hypersurface translates to these 6 conditions on the extrinsic curvature. And the extrinsic curvature evolution is usually okay, but the fact that the momentum conditions are quite weak for the canonical ADM formalism means that the Hamiltonian condition can grow. The quantities that appear in the Hamiltonian equation can grow really rapidly, and if they grow too rapidly, then they cause then basically because the Hamiltonian condition is the thing that's directly related to the lapse function. If those quantities grow too rapidly, the lapse function can decrease too rapidly, and eventually it decreases to near zero, and you get a failure of hypervelocity that way. So it's an analytical property of the equations, but it causes significant numerical issues.
Right, which by the way are probably reflected in the way that our causal graphs sort of kind of discretize space-time.
Right.
Probably the same thing going on there. But
right.
Okay, I have to go get my food in a minute, but I really want to go through this time-like singularity thing.
I have to leave now, sorry about that.
Okay, are you back later, Max? What is your?
Well, not really.
Okay, you're around this weekend?
Yeah. Let me
Right.
check. Well, tomorrow after 1 p.m. or so.
Okay. Well, maybe we can get in touch.
Okay.
Okay. Thanks. Okay. See ya.
See ya.
Bye.
Okay. Let's go back to this going horizontal idea. So your idea that there are space-like hypersurfaces that stack up.
Uh-huh.
What does that look like?
Well, that's the horizontal case.
No, but yeah, but what you're saying is that in this graph, what causes there to be causal edges that go horizontally? I don't know. I mean, causal edges going horizontally, we have causal edges going backwards if, I'm very confused.
Well, this is the max scan thing I was talking about.
Look at all these pictures. These are all layered causal graphs, okay?
Yeah.
I don't see anybody here misbehaving in that way. I mean,
Right.
you're saying that what we would expect. Well, actually, there are some horizontal ones there.
No, but the fact that you can construct a layering is not the question. That was the point I was trying to make earlier with Max, but I fear he maybe didn't understand. Look, the point is the layering has to actually mean something, right? So in order to be a space-like hypersurface, every point in space has to have been updated, right?
Yeah.
So if there is a max scan such that there are nodes that are not contained within it, then they have to they have to be updated on the next max scan, for instance.
Yes.
So now you have events on the same space-like hypersurface, but which have taken, but they're being updated on two successive max scans. So in particular, on the second max scan, there can be causal connections to things that were in the first max scan, even though some of the nodes are actually in the same spatial slice.
What will that look like in the causal graph?
Well, that's the horizontal lines thing.
Why don't we see any of those?
We're not. There's. What do you mean?
Why don't we see causal graphs? I mean, we do see causal graphs that have some horizontal lines in them.
But we're not constructing any. Our layouts of them would not support us seeing that anyway. We're doing a layered graph plot of them. We're asking for all the edges to be pointing monotonically downwards anyway.
As opposed to saying that
what we have to do is do a layered graph plot by generation, which is what the causal graph in multi-way system does when you include step numbers.
I think that's what layered causal graph does.
Yes, I think that's true as well. But if you just do a layered graph plot of causal graph, that won't do.
No, these are layered graph plots. These are layered causal graphs.
Sure. Okay. Then that's the right thing to look at.
Okay, so the claim would be that a time-like singularity corresponds to a failure to progress in time for a different reason than the space-like one where time stops. This is actually the opposite. This is time is just running.
Right, it's space that ceases to have any meaning.
Because it's kind of running sideways in you're jumping in space without progressing in time. Well, you are progressing in time. What the hell is happening? You've got oh my gosh, what is happening here?
No, so what's happening is that in the same way as so for the space-like singularity case, the space-like singularity is the situation where as you approach the singularity, spatial distance ceases to have any meaning, really, right? All that matters is time-like separation, and all that really matters is there is a singularity and it is in your future and you're heading towards it. And spatial motion doesn't really matter, right?
Yeah.
So in the time-like case, it's the same, but just flipped 45 degrees. So now what's happening is that the time-like singularity is everywhere around you in space, and it's and your motion in time doesn't really matter anymore. All that matters is whichever way you go, you're heading towards this time-like singularity.
Well, your time is happening. Time is okay. In this causal graph, you would normally be slicing the causal.
Time is completely dominated by spatial. Temporal distance is now completely swamped by spatial distance, and ultimately, all that matters is the fact that there is this time-like singularity, and it is in front of you, spatially.
Right. But in effect, time is stopping, but for a different reason. Well, time isn't stopping. You're running in time. You're just keeping going.
There are still causal edges. Yeah, it's space that's stopping.
Well, space is becoming meaningless because you're just going.
Right.
I don't get this yet. I don't get this. The failure to continue in the causal graph. Normally, you are making space by knitting together light cones. Your light cones have totally degenerated in this case.
Mm-hmm.
As you progress in time, I mean, the main point is there's no knitting anymore. You're going in your direction in space. As it turns out, it might be going in space, but the main point is you're locked into this thing that cannot knit.
Well, there is only one direction in space, and that's towards the singularity.
Yeah, which you in fact might never reach. Might be an infinite path. What happens at the end of your horizontal causal graph? You keep going there. Well, you're going down these edges. Chink, 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 chink. Then what happens when you get to the end of those edges, when you run off the edge of the edges?
Well, in ordinary GR, there isn't any such notion. The boundary is infinite.
I understand, but in our case,
I don't know in our case.
More thought is required. I need to get my dinner.
Oh, by the way, sorry. I don't want to keep you, but there are a couple of things you might want to see.
And from about what?
Function repository entries that I finished, or I mean, I haven't documented yet. But
okay, anyway, I would really like to see them. But can I talk to you again in like 45 minutes or something?
Yeah, sure. Okay.
Okay. Yep, why don't I'll call you back.
All right.
Okay. See you.
Great. Talk to you.
Bye.
Bye. Hi.
Hello there. Okay, so we're talking about time-like singularities, and we're trying to understand what that looks like. So, I mean, we think the space-like singularities, I mean, another pathology that can happen in our models is a closed time-like curve. The thing leads into a closed time-like curve.
Yeah.
So, I mean, even in the case of a...
Right. Or, I mean, a time-like singularity is a closed time-like curve which goes back exactly 0 time.
Okay, well, so a space-like singularity could lead to could lead into a CTC. In addition to being a terminal node, it could lead into a CTC, right?
Yeah, I mean,
I haven't seen that, but I just, I think it could happen.
Yeah, this is where it gets a bit tricky with terminology, because you wouldn't normally call that a singularity.
Well, I understand, but what is it?
I see what you're saying.
That's the question, right? I mean, in other words, I don't know why you wouldn't call it a singularity. It's a totally weird thing that can happen.
Right.
Okay, so you made a statement about the time-like singularity being related to being in a CTC.
Well, if you have a CTC that's degenerate, so it doesn't go back any time steps, just stays on the same time step, that's a time-like singularity.
That's a different claim, right? Because going horizontal.
Well, that is going horizontal. I
know it's going horizontal, but it's going horizontal in a way that is that you can go infinitely horizontal, right?
Right. So you can have, so there's, I think it's useful to distinguish between a kind of local failure of hyperbolicity, which is this degenerate CTC case, which is just an overlapping of space-like hypersurfaces, and the sort of global failure of hyperbolicity, which is, I suppose, what you would think of as being a time-like singularity. But the point is that, you know, that one is just a bigger version of the other.
Explain. So, I mean, here, if we had a horizontal, I'm really confused. I mean, by the time you're in a CTC-like curve, it doesn't make any difference whether you know, the time-like evolution just goes in a circle, basically. Whether the time-like evolution hangs down here or is rendered across doesn't make any difference. Because the future is just to live in the CTC. Right? It is a time-like curve. It's got causal edges in it.
Mm-hmm.
But that's different from what? How does that relate to the curve? Okay, let me show you something. I'm trying to understand this. Penrose diagram for a Kerr black hole, right? So we've got all these jolly diagrams. What is this critter here, where it goes in between? So the black hole, white hole story. What is that? And what is a white hole in our world? Is it one of our CTCs, or is it something different?
No.
What do you think it is?
No. My view hasn't changed since the last time we discussed this on the live stream.
What? Which is what?
Well, obviously, GR white hole is just a time-reversed black hole. That's what the Penrose diagram is showing you. So it's just it's a trapped surface, but with all the causal edges reversed. So it's a region of the causal graph where things can come out but can't go in. It's not a particularly deep observation, but
no, but I'm not sure it's correct. I mean, a white hole. So let's look for a case where that can happen. So you're saying there's a place in the causal graph where edges come out. So where there is a future light cone, but there is no past light cone.
In effect. I mean, I don't completely know when you talk about there not being a past light cone. It was terminology you were using earlier. I'm not entirely sure what you mean by that, but
Well, but let's understand what this would look like. I mean, so in this picture, right? If there's a white hole which has a bunch of future edges connected to it, future events connected to it.
Yeah.
What this is saying is that it has a very limited number. I don't understand this. Look, every event here has to be connected to the initialization event.
Yep.
Okay, so is it what it would look like is jung, 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 it's just going down one edge, it's not going down, and it reaches this event here somehow, and then kaboom, it explodes in a big display of causal edges. So that would be the opposite. That's not. That would be, it is a pre-trapped. It is trapped up here and untrapped down here. So it's initially trapped, later not trapped. That's what you're saying, I think.
I don't think so, but
well, so explain.
I'm just saying it's a time reversed black hole. You take a trapped surface, you reverse the causal edges.
Well, I understand, but I'm asking, can it happen in the time evolution here?
What?
Can it occur? Can you make a rewrite rule that causes one to have a white hole?
Yeah.
How?
I presume if you time reverse the rules that produce a trapped surface.
Yeah, then you'll see what I'm describing. I mean, you will see something where at the top, it is trapped within a small number of causal edges, right? But small number of events. then it will reach the point where it would have previously, where it will then be able to escape. Right?
But what does it mean to be trapped?
That it is propagating forwards here. And look, it could be that a given event, its future light cone, could be expanding and start covering everything. So what this is saying is, for a while, the future light cone does not escape to cover everything. So if you stopped at that, I mean, it's very weird, right? I mean, if you stop, see, what it would look like is, you know, imagine the time reversed version of one of these, right, wherever they were.
Yeah. Right.
Imagine the time reversed version.
Already a white hole.
Which is already a white hole.
These, because it's two-dimensional, and there's only and the black hole, the trapped surface also covers the boundary, so it's also trivially a white hole.
What? I mean, look.
Am I misunderstanding something? So it's, you know, if you have a two-dimensional, if you have a 1 + 1 dimensional space-time, and you produce a trapped surface in the middle that divides the universe into an interior of a black hole and an exterior, so both the interior and the exterior also overlap with the boundary of the manifold, then the black hole, the interior of the black hole can equally well be considered the exterior of a white hole.
Yes,
That's
I agree with that.
Basic
yes,
geometry, right? So the same thing is happening here, I would claim, unless you're thinking there's something that I'm missing.
Hold on a second.
Right. The place
You're saying that this here behaves like a white hole. It's spewing out a bunch of stuff here. This, this thing. Okay, so this.
What you're considering the rest of the universe in your black hole case can just as well be considered a white hole, with the black hole being considered the rest of the universe.
Oh, I agree.
Right.
I agree with that.
So the point is, they only become distinct either in higher dimensions or in the case where the interior of the black hole does not intersect with the boundary of the manifold. That's why it becomes a little bit difficult in two dimensions to distinguish between a black hole and a white hole.
Well, I don't know how many dimensions this thing is.
Yeah, right. Sorry, we're considering the trapped surface in only 1 + 1 dimensions. The actual space-time might be higher. We don't know.
No, I don't think we're considering it in any number of dimensions. We're just saying the trapped surface is just asking the question: does the light cone expand or not?
Right.
So I don't think we're committing ourselves to that. But let me just understand this for a second. So the claim is that looked at from inside here, this part here looks like a white hole.
Right.
Because this part here is spewing edges into this part here.
Right. It's a region of space-time in which all the light cones tip away from it.
Yeah.
So even in this case, I mean, okay, the place where you could convincingly get a black hole and a white hole and make distinctions between them is the case where instead of subdividing the universe into the interior and the exterior, it subdivides it into an interior and two exteriors, or at least two exteriors.
Sure. Explain to me, in the case of the Kerr black hole, where you have this crazy alternation, which I don't really understand. Yeah, I'm still not okay. So that, I mean, basically, we're saying a white hole is something where you start with a small number of edges. What's the difference between? Oh my gosh, what is the difference here? Well, okay, I think I more or less understand. But let's come back to this question about what a time-like singularity really is. So we've got several different ideas here. And, you know, again, I'm still trying to understand, in the general relativity case, what is the definition in the Penrose diagram of what is a time-like singularity?
I mean, other than just telling you that it's a space-like singularity rotated 45 degrees, I mean, I don't really know.
Well, okay, but what does it mean? What do the light cones do at that singularity?
Well, they're not defined.
What do they do as they approach that singularity?
They well, they tip over in principle.
But don't they degenerate as well? Don't
Yeah,
they?
I mean, yeah.
But so, you know, they were cones, and I would assume that when they reach, I mean, at the space-like singularity, they squash up because there's no time. The time has stopped.
Mm-hmm.
There is no time extent.
Right, and in the time-like singularity, they fold, you know, they sort of open up like a flower or something, right? So then the notion is there's no space. There's only.
Why is opening up like a flower corresponding to no space? Why isn't it instead they scrunch down so that they're only in the time direction with no space direction?
Why would they be only in the time?
Well, because that's what I would think that
the time-like singularity is the notion where it is the place where all spatial directions lead towards the singularity. You know, the notion of space is completely replaced with just this inevitable singularity.
Okay, well, hold on. So let me understand. So in the case of a space-like singularity, what we're saying is that all time, eventually time stops with everything led to a particular place in space. Right?
Mm-hmm. Okay.
I think so. I mean, it's like, whereas what you're saying is in the time-like case.
That's not how it's formulated in GR.
What is it? How is it formulated?
Because you know that the notion of time stopping implies that there is anything sensible you can say at the singularity. In GR, the way it's defined is it's the place where time, you know, time-like distances completely dwarf space-like distances, and so, in effect, the notion of space-like distance loses meaning, and you just enter the space-like singularity just becomes this thing that exists across, you know, in all possible time-like directions. They all converge at that singularity. In effect, it ceases to become a place in space. It becomes a place that just exists in the future.
Sorry, I got distracted for a second. Could you repeat that? I'm sorry.
Yeah, sure. So it's a space-like singularity as you approach it, the notion of it corresponding to a place in space doesn't really mean anything because the idea is that time-like separation is the only thing that matters. Space-like separation is completely dwarfed by time-like separation. So the singularity, which starts off as being a particular place in space, instead becomes a point in time that necessarily exists, kind of irrespective of your time-like direction. Doesn't matter which time-like direction you move in, you will reach the singularity.
Yes, I understand. Time-like direction. Let me think. So, in our causal graph, I'm trying to understand whether the fact that we're seeing only these single point singularities is surprising, because you're saying in all directions, in all time-like directions, lead to the same endpoint, right? Which is a terminated endpoint.
Yeah. So in the causal graph, it would be a funnel in the causal graph that leads to to some local normal.
That's what I was expecting to see, right?
Yeah, me too. And right.
Yeah. All right. Okay. So I mean, this is a funnel in the causal graph.
I mean, I agree. I'm not. I think it is a place where time stops in this formulation of it. But I just wanted to point out that that's this is a more powerful formulation than standard GR. So that's not normally how they're thought about.
Okay. So, but again, one would think that a time-like singularity would be one where space stops.
Yeah.
But I just don't get that yet. I just don't understand yet. I mean,
so it's a point in time where irrespective of which spatial direction you go in, the singularity is in front of you.
But what the heck is the singularity? I mean, the fact is that you keep going on causal edges, but the causal edges you're claiming are, you can't escape. I mean, look, maybe what this is, okay? So here's a possibility. I don't think it's correct, but a possibility is that it is a completely isolated line, right? That you'll never reach anything else. So that's what you're saying here. This is something where every line is isolated. You'll never reach anywhere else in space. Right? You keep going down. Yeah, this is what it is. This is right, I think. You keep going down a causal line, but you can never get anywhere else. And that happens in this tree case as an example, right? You keep going down this line and you keep going, but you never reach anywhere else in space. And one could imagine that could happen. One could imagine, look, here's an example of how that could happen let's just see how it can happen. Can you get a causal graph that is just a single line, no branching? If I just say A goes to A here.
Yeah, I think that's probably.
Yeah, there we go. So I think that is our time-like singularity. I think that's it. I think it's something where you go, and that's the analog of the space-like singularity, where where time stops. This is like you never reach anywhere else in space. This makes sense to me. I think this is right. Now, this creature is a rather strange creature because that's saying this is kind of a whole, arboretum of time-like singularities, so to speak.
Right. As would any neighborhood independent substitution system be.
Indeed. But so what's the interpretation of that in general relativity?
Well, it's the analog of a sort of superluminally expanding universe, but it's superluminal expansion in the time-like rather than in the space-like direction.
Okay, but is that an existing? I mean, because this thing here, This is definitely, this is right. This is a direct analog. I think this is right. So in what sense? Yeah. I don't really understand. Don't you think this seems right? I mean, this is the kind of the analog of, this is no space. The other one is no
no,
time.
I'm coming around to it. Yeah, it makes sense to me.
So, okay. So then let's come back to this guy here.
But hang on, this is the same.
Which one is the same?
This is the same as the thing I think I've been saying, right? That if it's a causal line, a single causal line that only updates a single point in space, then because all the other points in space aren't getting updated, they all must lie on the same layer.
Let's look at an example. Okay, so we're saying something like A goes to B, A goes to like this. Whoops.
That's not, it doesn't match the initial condition.
I don't know what that means. What does
But
that mean?
You understand what I'm saying, right? That the point I was making earlier, that to define a space like hypersurface, everything has to get updated. Every point in space has to get updated at least once.
Yeah, I do understand it.
But if you're only updating one point in space, they all have to lie on the same surface. So I think we're both right.
I think you might be correct, but let's see this as an example of can we make something here where we're saying, wait a minute, I want to say A goes to A here, and then I want to say B
we could
goes
do something.
to B.
If we do something like. Yeah, okay. So I guess if your universe only consists of time-like singularities, then it doesn't quite make sense.
For what?
That my interpretation of it doesn't quite work in that case. But I think in other cases.
But how can you get a combination? So let's understand the combination case.
Oh, easily, right? Because if you did an A goes to, if you do an A goes to A goes to B, and then B goes off and evolves in its own merry way. Like, wouldn't you get? Yeah,
no.
What's going on here?
Well, remember, this is only a particular updating order.
Oh, yeah. Oh, and it's sequential, so it's only updating the A's and...
I'm sure the multi-way analog of this will have all kinds of other things. I mean, the multi-way analog will have something here that goes off into la la land.
Right. Yeah, okay. I need to build up some intuition for this.
Why didn't that work? Oh.
That's a period.
Psi. Oh, it's a states graph. We don't want that. We want an evolution graph.
We also want to see the causal graph in particular.
Oh my gosh.
Great. Oh wait, yeah, because
this thing is a
But that's an indication of the time-like singularity. right? The fact that it's just looping onto itself.
Yes.
So there's a lot of other stuff going on, but then there's also just this one isolated thing that isn't connecting to anything else.
Well, and what you claim we would see
So
in
if
this
we
case.
wait, hang on. Okay. Right. In fact, if you go back to the one above and you just do an include step number true, include step numbers true.
This one here.
No. I mean, the one with all the that one.
Doesn't seem to help.
Hang on. Instead of step number.
That does help. The hell is that doing?
Oh, but it's still connecting to a lot of other stuff. It's not quite what I wanted.
Right, you thought it was going to have a streamer that was a bunch of A's.
But obviously that's not going to happen,
Well, but the fact that that's not happening is a quantum statement about this horizon or this singularity.
Right.
Right. That is the singularity being quantumly entangled with other things.
Yeah.
So, because what I had hoped we would see. All right, so a space-like singularity. I bet if we take, let's take our favorite sock here. Okay, I think I've got a smaller sock up here. Well, let's take the big sock. Okay, so this.
You didn't copy the resource function.
I didn't mean to, because I'm trying to make a multi system.
Oh, right. Okay. Yeah, sorry. Fine. Will make sense. I think you need one extra set of braces around the rule.
This rule here.
I think so.
Okay. So now I want to make the causal graph here, presumably.
Sure.
Oh my God. Oh, well, that wasn't very. Oh, causal graph structure. Okay. Okay, let's say. Come on. Find your socks. There's more steps. There's like 10 steps over here. Let's try the simpler one up here. Wow. Happens between 6 and 7. That's weird. Unless we hosed something, or unless the thing sort of blows up there.
Wait, weren't we already on 6?
Yeah, that's why I'm very surprised that it isn't working.
No, I'm saying we computed 4, and then you tried computing 6, and then that was when it hung.
Oh, really?
I think so. That was the last one we actually got a result back for, I think. You very boldly went from 4 to 6, which
I see, fair enough.
That looks pretty disconnected to me.
And by disconnected, we mean?
Well, I mean, there's a multi-way cosmic event horizon thing. It looks like. Is there any evidence of socking?
No, but it didn't go long enough to sock. But what does it mean when there's a multi-way cosmological event horizon, cosmic event horizon?
Well, it means that there is a cosmic event horizon in the
entanglement space.
Yeah.
What the hell does that mean?
It means that there are things that can't get entangled.
Indeed.
Because your Hilbert space is growing too rapidly.
Right. But so what would we expect to see? I mean, the original idea here was that we were just going to zoom right into quantum black holes.
Uh-huh.
Unfortunately, there's not a lot of zooming that was happening here.
Yep.
Okay, let us see the formation of the sock here. Oh my God. It will be interesting to see in the future how well people manage to get through, how much there's just going to be irreducibility just in your face everywhere.
Right.
So, I mean, some things, we have no idea what ends in a sock here. Let's try and get to 7. And maybe we should try some things that actually have shorter termination times, even shorter termination times, because maybe they don't even terminate always.
Right.
That, to me, the presence of termination in the multi-way causal graph the presence of a event horizon or presence of
okay, can we analyze this?
Well, let's try and get another level. While we're thinking, let's have the computer think as well.
Right.
Well, I mean, there are things here. Who knows whether that will actually terminate like that? Right. Something better terminate.
Yeah.
What we expect to see in a black hole is also an entanglement horizon, right?
Yep.
We expect to see something, well, actually, this is interesting because I don't think there's much more there. It didn't grow, did it? No, it did grow.
It did. It's just that maybe I'm just jaded, but all multi-way causal graphs basically look the same to me.
Oh, no. They have a whole inner life. It'll be easier when we have this in VR, I think.
Huh. Yeah, I agree.
Where you can just pull it around. Actually, this thing, I think it's worth doing 3D visualization on. I think this will be somewhat revealing. Notice that there are kind of prongs coming out there. Okay. Okay, but what we expect to see in the case of a physical, did we just get the result?
It looks like we did we?
And it looks like it's terminated.
Yeah. So it has.
All right, let's try looking at this puppy in 3D.
Did that help?
No. What a useless object. I mean, what the hell is this?
Can we do our causal connections testing on this to see if there's a SOC region?
Yeah, probably. Let's try and look. I think my dead end finder will work.
Oh, yeah, okay. Yeah, good point.
Well, and I can already answer it. Look, there's plenty of dead ends. You can see them all down here.
Right. But I mean, we also have things for detecting these kind of, the incoming but not outgoing things, which we're seeing in the space-time case. Maybe that's not
outgoing. No, I think, but we have exactly that. I mean, this is the we have edges here that clearly terminate in. Okay, my question really is, I mean, let's take the most trivial example we have, like this cosmological event horizon. What do you think this is going to look like in the multi-way case? You know, I should take even more trivial ones because this is already going to be very, very, very complicated. I'm
going to predict. Yeah, there should be multi-way causal disconnection as well.
I think so too. Yeah, I think so too. Yeah, right. So
whether we can evolve it far enough to see that is another question.
Yeah, we can get simpler examples where there's causal disconnection there. Oh boy, there's a tornado watch around here, which is very unusual.
Oh, wow.
I can see, let's see, my wind speed meter. Oh, it's nothing. 8 miles an hour, it says. That's nothing.
From what I know about you, I assume you're well kitted out to survive tornadoes.
Well, ultimately, yes. Oh, there, it just jumped to 10 miles an hour. I have this, okay, what did it do wrong here? Oh, that's
the initial condition. Mm-hmm.
Now, the real question is whether this is well set up enough that my phone is going to start making, if there really is a tornado thing here, you know, in many parts of the world, your phone starts, you know, the weather system starts giving you phone alerts. Oh, lightning. Okay. Still only 10 miles an hour wind speed.
My gosh.
Well, let's try simple graph on this. Oops, I need to go inside there. Okay, hold on. Let's see whether we can get another level. I mean, the issue is, what does a cosmological event horizon look like in the multi-way graph? Because it should have hit it by now. It's got enough steps, it should have hit it. I think there's going to be separation between these two sides.
Yeah.
And basically, when there's, I mean, we made a claim, which I don't necessarily believe. I mean, clearly, okay, actually, you know what else we should look at? We should look at the case where it actually separates. One of these cases like this, where it actually separates the.
Yes. Yeah. As the most clean-cut example, I agree.
Yeah. I've got simpler examples of separation, actually. Let's take a look. Okay, let me go look for one of those. I did not think this was going to be this complicated. But then I hadn't. There we go. There's the minimal one. Okay, what the heck is going on here?
Look, you're getting termination points.
Yeah, I can see that. I mean, bizarrely, the thing looks awfully like its spatial analog.
Right, right. So what's happening is, I mean, because that rule can apply to the individual thingamies, right? Once they've each loop,
yes,
can evolve, so that there are going to be causal connections there. It's just that this kind of makes sense. I don't know.
Well, here, let's look at it. Let's look at its ordinary causal graph. Okay, so that's its ordinary causal graph. What the heck is going on here? So it's multi-way causal graph. In spatial disconnection, the multi-way causal graph cannot possibly be connected. By the time those things are separated, it's toast. Can't ever reconnect. Branch like whatever. I mean, it's just completely disconnected from that.
Mm-hmm.
Do you understand this? I mean, this is, what do these mean? I mean, those in our current interpretation, those are space-like singularities. Well, there should be branch-like singularities. What is a branch-like singularity?
Well, a preserved pure quantum state.
Fair enough. Quantum state, in other words, i.e., it doesn't move in branchial space. i.e., it doesn't entangle. Okay, so is there a more trivial disconnection case? Let's just see what this does. This will be bonkers, I think. But let's just see what it does anyway. Actually, I have so little experience with multi-way causal graphs. Okay, that's one which has a normal form. That's the sorting system, isn't it? What is that one? No, maybe not. Oh, look at that. That's one which has what we have identified as a time-like singularity.
Right.
In the causal graph, it has two separated pieces. Ultimately leading to a bunch of space-like singularities. Or are they branch-like singularities?
I suspect they're both.
Perhaps.
Because, I mean, space-like singularities are branch-like singularities, but not vice versa.
Okay, look at this. This seems relevant. So this is showing for each of the I mean, the fact that this section just ends with no comment on this object is it's similar to the treatise on the Cirripedia.
That's a reference that's beyond me. Hang on, but
oh, that was Darwin's the book he worked hardest on.
oh, okay.
The treatise on the Cirripedia, which is a study of barnacles. Okay, so let's look at this. My God. Okay, so roughly what's happening here. In many of these cases, the multi-way graph from all these different states is disconnected.
Right.
What do we think is going to happen? Okay, so what I find interesting here is that even though there's total spatial disconnection, there isn't, as we would expect, branchial disconnection. There are, however, branchial event horizons of various kinds.
Yes, right. I mean, there is sort of branchial disconnection, right? I mean, you can see there are a bunch of causally disconnected branchial regions.
Sure, but those have entanglement horizons.
Right.
Right. So what this is saying is, okay, so let's think about what this might look like for your communal garden black hole. Okay. What we would expect there is that, again, there are entanglement regions that you don't, I mean, it might be a cosmic event horizon or it might be a black hole event horizon. We don't actually know. Right. For a black hole, do we know whether it's entanglement horizon, what type of horizon its entanglement horizon is?
Well, I mean, it has to be a black hole type, doesn't it?
It's not obvious to me.
Because I think, well, I only say obviously because the multi-way causal graph contains all of the space-like, all the space-time causal edges. So if there are space-time causal edges pointing in towards the interior of the event horizon, then they will.
Yeah, but so what? There may be still other pieces to this branchial. Well, what are you saying? You're saying it must decompose into these one-way causal graphs, because that's essentially what the black hole thing is. It's a one-way causal graph.
Yes, right. I'm saying it can't correspond to a cosmic event horizon. right? Because we know that there are at least causal edges going in, and those have to be preserved in the multi-way case.
Well, who's to say there's just one event horizon? I mean, in other words, you're saying there exist.
Okay, yeah, fine. Fair point. There might be a cosmic event horizon kind of hanging around somewhere as a result of something, but there has to be at least a black hole-like entanglement horizon if there was an ordinary black hole event horizon. I think.
It's not obvious to me. I mean, so just roughly what is this going to look like? So it's going to look like at the entanglement horizon, basically, let's assume it's a cosmic event horizon, okay? So at the entanglement horizon, things separate How does the Hawking radiation work?
So you get, so at the entanglement horizon, you get some branch pair that's produced in that vicinity. And so one element of the branch pair is on one side of that horizon, the other element is on the other side. Or in other words,
let's walk through that.
One is, yeah.
Yeah, because I mean, we're not, in the case of the ordinary horizon, you're saying there exists an event such that one successor event is inside the trapped surface and the other is not.
Yeah.
Okay, so you're saying the same thing happens here.
Right. Right. And the point is that if those two events happen to correspond to creation events for two elements of a branch pair, then that means that one, that one branch pair can escape, one element can escape.
So what's the space-time analog of that? A single event spawns two photons. One escapes, one does not. The difference is that's not happening spontaneously.
Right, right.
Although actually in our model it probably does.
Yeah, I mean what it implies is there's kind of like a vacuum energy Hawking radiation that is completely classical.
Yeah, I think so. I think so. So I mean let's look at that.
Black holes radiate classical dark energy.
Right. Okay, so the branchial case is one event can spawn two others, one of which is trapped, the other is not. Okay, now there's the spatial case.
Yeah, I mean, so this dark energy Hawking radiation, this is just one. That's just a way of saying that there is causal disconnection, I think.
Well, let's think about that for a second. So there are events. Yeah.
What's happening in the multi-way case is, this is a mode of failure of causal invariance, right? You produce a branch pair, but they can't reconverge because one element is causally disconnected from the other.
Yep.
But we already kind of found that, or we already established that combinatorially determining causal invariance is exactly the same problem as determining causal connectivity, just in the multi-way graph as opposed to the causal graph.
Yes.
Right. And so all you're saying here, I mean, I think this will end up basically being a somewhat trivial statement that says, the minimal, just like the minimal unit of failure of causal invariance is an unresolved branch pair. You're saying the minimal unit of causal disconnection is a sort of event pair, causal pair.
All right. Minimal. Yeah, I agree.
Yep.
Of causal disconnection is a spatial branch pair. It's a spatial pair. Right. Okay, but let's walk through that for a second, because we have a different thing going on, because we're making space, right, in a way that ordinary general relativity does not. Because all the time, there's activity in space. These spatial pairs are being made just by virtue of making space.
Right, right. And so this is this is why I mentioned the sort of dark energy.
Oh, I
thing,
know,
right?
I know,
It's
I know,
like,
I know. It's radiating olygons like crazy.
Right, because basically, what's happening is that the dark, for any piece of dark energy in usually in the universe, you can see its whole light cone. But in this case, there's like half the light cone is missing because it fell on the other side of a black hole. And that's a very weird thing.
Hold on. Let's think about this for a second, okay? Because, there is a possibility. I mean, if black holes in the center of galaxies were spewing out dark energy, that would be quite interesting. If there's an analog of the solar wind that is dark energy from a black hole, that would be very bizarre and quite interesting.
Right.
Okay, so let's look at this for a second. Okay, so what we're saying is we've got this black hole, and it is it's got a bunch of pairs. Well, let's look at our pictures of black holes back up here. Okay, so our friendly black hole here. Oh, I see. If I go higher up here, I will find a branch pair. If I go to this node here, I will get to a branch pair where some part of the branch pair goes into where some part of its future light cone is here.
Mm-hmm.
So, among other things, momentum conservation
Uh-huh.
is curious for this.
Right.
I mean, so there is so these things there is an energy density, which is essentially vacuum energy.
Right.
Okay. Then there should be momentum, right? Because the momentum, the thing's got, what's that?
Because it's not just going straight down.
Well, yeah, but in particular, it's losing one of its momentum legs.
Yeah.
There should be net momentum. Generated by the uncancelled causal edge, basically.
Right. Hawking radiation implies that the black hole radiates mass, and vacuum radiation implies it radiates momentum.
The radiation of mass up here is a consequence of
an assumption that may or may not hold in our models. So I'm not even sure if they do radiate mass. Well, I mean, conservation of energy.
Yeah.
But if we're already kind of saying that causal edges, that we're allowing for unpaired causal edges to kind of create new energy in the form of vacuum, then the
Well, I don't
argument.
think we look, Hawking radiation. Let's call a spade a spade. Hawking radiation has never been observed, right? So we don't actually know what happens.
No. But the reason I'm finding this interesting is because it potentially gives us a different prediction about Hawking radiation.
Oh, it does.
That,
Yeah,
that actually it might emit. The black hole might be emitting particles, but it might not be getting any smaller.
Yes.
Which would be kind of interesting.
Sure. Okay, so question. Could the black hole emit particles without losing mass?
Right.
Okay, so that.
And if we allow this, then we have to address the difficult topic of vacuum momentum and what the hell that might mean.
Why? I mean, there's there's local vacuum momentum, but that doesn't have to be global vacuum momentum.
But the local vacuum momentum, I mean, that will become causally connected to the rest of the universe, right?
Sure, the local vacuum momentum, but it's streaming out in all sides from the black hole. It's a wind.
Right.
It's just wind.
Right. Fair enough. Okay.
I mean, basically, this would predict essentially a wind of oligons from black holes.
Right. Which, yeah, okay, fair enough. Which could be interpreted as a vacuum momentum.
Sure. Now, the question is, what is in that wind? And is that wind, if it doesn't interact with anything, it's just spewing momentum out of the black hole. And it's unclear what consequence that has.
Mm-hmm. Right.
Okay, let's think about this for a second.
By the way, I'm going to have to leave reasonably soon.
It's really late for you. I'm sorry to keep you up.
No, that's okay. I'm happy to chat more about this over the weekend if you're
around. Well, let's do it. Yes. Okay, just hold on 1 second because we're just about to discover black hole winds.
Yeah.
Why is the spatial case not considered by people otherwise? Oh, because basically they don't get spontaneous, there is no spontaneous activity in the vacuum normally.
Yeah, or in other words, light cones aren't generally physically instantiated, so to speak.
Yes.
The idea that there is a dynamics of light cones and that is somehow prior to the dynamics of actual space-time is not the general approach.
Right, light cones live in space-time. They don't make space-time.
Right.
So hold on. So what happens here? So we get these light cones are being created all the time. And these kind of unchecked pieces are coming out. So it's really a wind of space-time that's coming out of the black hole.
Right.
It's making a bunch of new causal edges which have momentum and energy. What the hell does it do? So it's like this black hole is taking what would normally be, hold on, it's taking what would normally just be an equilibrium in the vacuum.
Yeah. And it's removing half the light cone. Yeah, exactly. I'm trying to I don't know. Is there a mathematical term for like half a cone? What is it? What is that called in geometry?
I have no idea. A piece of a there is a name for that, actually. There's a name for, it's not a frustum because that's cut the other way.
Oh, yeah, okay.
It's a conic section.
Yeah. Which conic section is it?
Well, I would say it's the parallel lines conic section if you cut it halfway down. I mean, if you cut it in half.
Right. Right.
But okay, so anyway, so we've got this cone and it's being cut.
Mm-hmm.
Part of the stuff in space goes into the black hole, never to be seen again. Part of the stuff in space is uncancelled and stays outside.
Right.
The whole thing has a certain energy density. I don't quite understand why the thing, okay, what does it, the fact that it has an uncancelled edge, I mean, it's almost as if the black hole is just coming through space-time, just punching a hole through. And the presence of particles, or the presence of a wind, so to speak. So I see, when it punches the hole, it's leaving behind uncancelled momentum, which would otherwise be in equilibrium.
Mm-hmm.
So that uncancelled momentum streams out from the black hole. It's not clear that it has mass any different from the mass it would otherwise have, because all it did was to chop its volume of space-time out.
Right. As you say, the probably the only measurable consequence is the local breaking of equilibrium.
Right, and the local breaking of equilibrium leads to momentum.
Yeah.
You know, here's what it is. That momentum, I predict, will have a gravitational effect.
Mm-hmm.
That momentum would be analogous to local expansion in the universe, I think.
Right.
In other words, what's going to happen is, it's as if around a black hole, you know, potentially around a black hole, it is as if there was local expansion of the universe. So the black hole is there, and it's like puffing outwards the stuff. I don't think it necessarily has any particles at all. I think it's just a feature of space. I think it's like a miniature.
Yeah. I agree. I don't think it has to be associated with oligons. I think it's a pure vacuum energy thing.
Yeah, and it's what it would be is local expansion of the universe, a local metric that you could probably model with an energy momentum tensor. Just saying there's momentum there.
Mm-hmm.
And in particular, there's a coat of momentum. So basically, and then there's continuity equations of momentum. So I don't know quite how that works, but it's as if there was a coat.
Well, the continuity equations assume continuity of causal edges, which is obviously broken at the horizon.
Sure, but
I'm going to claim that basically it will act like the horizon will act like a momentum shockwave.
Yeah, well, fine, but I mean, away from the horizon, the question is, does it stream outwards, or does it somehow?
Yeah, I mean, obviously, once it's past the horizon, then it's subject to the same continuity relations as anything else. So I think it will then become causally connected to everything.
So it's making a suggestion that around a black hole, I mean, will it act like negative mass? See, the black hole is going to have lots of gravity pulling things in. What's the difference between the gravity that pulls things in and this momentum flow? I mean, it will change. Basically, what this will do will change the vacuum, the Einstein equations to not be vacuum Einstein equations right outside the black hole.
Yes, yeah. Although it's worth bearing in mind that this effect is presumably tiny.
Why?
Well, because it's at the level of single causal edges smeared across the entire, black hole surface area.
But I mean, there's space knitted around the whole thing.
Yeah.
Well, your claim is the effect is small. Okay, claim.
It's a causal edges don't carry a huge amount of momentum.
No, I understand. Effect is small because it is the area compared to the volume.
Right. Yeah. So yeah. Obviously, the bulk space-time properties are volume properties. The horizon is an area property. So just like with the Hawking just like the fact that Hawking radiation is very low temperature, this effect, I presume, my intuition says, is going to be pretty small.
Right. Because it depends on the area.
Right.
But it's basically classical Hawking radiation.
Mm-hmm. Right. And is presumably not something that has been considered in the context of holography, but I'm very interested to know what its holographic dual would be.
Explain.
Well, I mean, so that the basic sort of philosophy of gauge gravity duality is that stuff that goes on at the horizon has a dual that's sort of a part of the bulk theory on the interior.
Right.
If this is a feature of the black hole event horizon that hasn't previously been discussed, then if gauge gravity duality is to be believed, then it should have some dual on the inside, and I don't yet know what that is, or if it even makes sense to ask, given that it is a classical phenomenon.
Oh, the fact that it's classical, I wouldn't worry about that. The question is whether.
I mean, obviously, it has a trivial dual in the sense that for every causal edge that's coming out, there's a causal edge going in. But I don't know.
I think it'll be a Gauss's law for causal edges of some kind.
Yeah, right. It has to. I think. Yeah, I agree. Essentially for vector analysis reasons, the fact that this thing is happening has to imply some feature of the bulk geometry on the interior. But I kind of want to know what that is.
It's a divergence of causal edges. Somehow.
Sure.
Maybe. Or maybe. Yeah, I'm not sure. Anyway, you should go to sleep. And
just before I go, by the way, I want to show you something.
Yeah, please.
Quickly.
Yeah, okay.
You want to share? If I share for a sec? Yeah.
Yep.
Okay, so none of these are documented yet, but okay, this is multi-way combinator, which can, in its basic form, will just return an association of combinator rules for a given combinator system.
Can you run it?
Yep. So if I do that,
is this in the Dropbox, by the way?
No, but I'm about to put these on there, and I'll try and document them this weekend and get them submitted to WFR by next week. So I wrote state and event rendering functions, as you can see. So if I do that or something, so I think now everything that's in multi-way system should now work for the combinator case.
That's cool.
Then I have the same. Oh, that's something else. This is the same thing for Turing machines. So if I do states graph, the rendering functions I wrote for the Turing machine case are not particularly great. They're just doing array plots of the state and the tape. But if I do evolution causal graph, that should work. The rendering takes longer than the actual computation, but that's what that looks like.
It's very cool.
Then, rather excitingly, there is this. So, okay, so there are two functions, quantum multi-way compile and multi-way quantum compile. I might have to rename those if they're too obscure. But so quantum multi-way compile takes in a specification of an operator and a quantum basis, and it compiles it out to a set of multi-way substitution rules. So this is for a quantum Fourier transform, and so on a single qubit. So if I now apply this, I can do quantum multi-way compile and then give it an initial set of states, and I can do this, and it will output that. And so that's what I would have if I take this operator and I apply it twice. So this is 1, 0, and 0, 1. So if I just apply it twice to 1, 1, then I would get 2, 2, which is, so if you cancel out the 1 zeros with the minus 1 zeros and the 0 1s with the minus 0 1s, you would get, you see it, the vector you get out is the same.
Do one more step.
Sure.
The quantum.
So if we do that, if I do this is now 4, 0. So you can see this is canceling exactly with that, and we're left with 4 of this because of 6 minus 2.
Why is there a minus? Wait a minute. Why is that cancellation happening? Because that's your coordinates in. I don't quite understand. The 2 and the 6 are branch weights, are path weights, right?
Yes, right.
Okay, so why is there a cancellation?
So the cancellation is happening because because there's this thing with this phase and this thing with that phase, and if we were to plot this thing out sort of conformally, they would be at 45 degrees.
So you're saying the superposition of those two things.
Yeah.
Why are they at 45 degrees rather than 90 degrees or 180 degrees?
Wait, sorry.
I know 180 degrees.
Well, it depends on your conformal sort of.
Right, but okay, but we've got these path weights, but then I don't understand how to interpret. You're saying that the superposition of the thing on the left with the thing on the right.
Uh-huh.
I don't understand how to apply the. I mean, because we're saying the position, the value in there gives us our position in branch Hill space, right?
Yes, effectively.
Okay, so how does that affect? I mean, it's all well and good that those things are in opposite directions in branch Hill space.
Mm-hmm.
But how does that then give us a 0? I mean, what are we trying to get at? We're trying to say that it is we're trying to claim.
So I mean, these two things. I think we discussed this over the phone, right? That these two things effectively cancel, because if you wanted to measure, if you wanted to construct a branch-like hypersurface that contained both of those states, it would have to contain everything else in between.
No, I realize that. I understand that claim.
Mm-hmm.
I think we need to make that more precise. I mean, so the basic claim is, but those other two in the middle.
Yep.
I don't quite understand why we can just take the path weights and subtract them.
Yeah, I mean, to show that actually operating, I'm going to need to simulate the measurement step as well, which is my next project.
I think you might want to call this quantum 2 multi-way compile.
Yeah, I was thinking about. I couldn't decide if that was too clunky, but I agree that's probably a nicer phrase. But it means that we can now do.
What is that?
That's the evolution causal graph for this sequence of Fourier transforms.
How do I see that it's a Fourier transform?
You
just run it for like, I don't know, 6 steps or something.
I mean, it's now gonna repeat itself because this is a pi/2 phase thing.
I see.
So that should now be 8. 8, yeah.
But so, how do I make a non-trivial quantum circuit here? I mean, if I...
Well, so you can compose any collection of operators you want. So if I don't know, let me invent something weird. I have no idea if this is going to make any sense. Okay. Moment of truth if I do 1, 0, 0, 0. Let's do 0, 0, 1.
Why do I need multiple things? I could start with a single quantum.
You don't. But I just, it's more interesting to do it with superpositions of basis states rather than just basis states.
Let's just do a basis state for now.
Okay. Let's do an evolution graph. So this is a more complicated quantum circuit, but it's also it's a lot less clear what's actually going on.
I still want to know, when we make that measurement, what do you think that's going to be like? So how will you describe the measurement process? What do you think you're going to do? Are you going to do these completion things or what?
Yeah, that was my plan.
So let's walk through how that would work. So you're saying you're going to do down at the bottom and the output from this.
Yep.
You're going to try and coordinatize this somehow. I don't quite get this. What do you think you're going to do there? So I don't get this. How this is going to work?
So what should happen if my geometrical intuition about interpreting completions as projections is right, is that if we attempt to do a completion between these two things that are that are sort of exactly out of phase, then the consequence of that completion step will be 0, 0.
What do you mean? What do you mean? I don't understand that. How can you work out? I mean, what does the completion have? Anything? Completion doesn't know zeros and ones from a hole in the ground.
No, sure. But what it does know is, so in this minimal kind of qubit model, right? There are only zeros and ones in your state vectors. So there's a position 2 here. There's a 1 there, and there's a -1 there. Those two things are not reconcilable. The only common thing that they can consistently reconcile to is 0.
Okay, so you're saying the completion,
whereas 1, 0 and 0, 1, they can reconcile to 1, 1. There's no conflict there. It doesn't care that they're zeros and ones. All it cares about is that -1 and 1 are different.
Okay, so you're claiming that, but the fact that those are lists is also, does it really care that they're lists?
No. And in fact, that's why I'm going to have to change the way the Knuth-Mannix completion procedure works a little bit so it deals with this case correctly. But that's my next.
Okay.
job.
Okay, but I mean, so then all it's going to do is it's going to look at the rules, the original rules.
Yep.
What's it going to say? It's going to say, I see, it's going to be, but it does know their lists in the sense that it can unify pieces of those lists, right?
Yeah. It just needs to know it's a thing with 2 elements, and those elements have taken from some finite alphabet. But at that level, you can basically think of it as being a string system. And so yeah, and then the point is it's going to try and collapse it down to a single state. And in doing that, it's going to try and unify a bunch of these things. And those things which it can't consistently unify will end up being reduced to essentially 0, 0.
Why? I mean, they'll be reduced to some. I don't know how does 0, 0. It's just a position in branch Hill space. 0, 0 is just the origin of branch Hill space, isn't it?
But it's you keep talking about coordinatization. Obviously the completion procedure doesn't know anything about that, right?
Yeah,
0, 0 is just the empty string.
Okay.
Right. So it's that we have empty and then -1, empty and 1. The only way to resolve that symmetrically is to go empty, empty.
Okay.
So that's what the completion procedure will do. I don't know. I'll write it. Then we can.
Yes. Well, very interesting. So put these in Dropbox. Yeah.
Yeah, I will. And then so then the multi-way to quantum compile is then doing the opposite thing. So if we take some arbitrary string substitution system like that, it will compile it into an operator basis specification of this kind. So in this case, it's using the string basis of A, B. And then if we do multi-way quantum compile that, so this is now running the this is taking this operator, applying that to this basis, and then doing the linear algebra to work out that it's A, B, 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 and then we can compare that against the actual multi-way evolution, and you can see that it is in fact 1A and 4 Bs. In this case.
So wait a minute. So that's taking the multi-way system and trying to.
So in this case, if we take what we're saying is if we take this operator, we do matrix power that 3 dotted into.
I don't understand how this works when it's beyond just a neighbor independent substitution.
It doesn't have to be neighbor independent. It just has to conserve the number. It has to be trivially unitary. It has to conserve the number of states on each evolution step.
Well, very interesting. All right, I don't completely get this one, but I mean, I see what it's doing.
Yeah, I mean, it's just inverting this.
Yeah.
But
all right, we got to nail down this thing with what it means. Path weights versus turning in branch Hill space, and how this idea that the superposition of two things that are in opposite directions in branch Hill space that gives 0.
Mm-hmm.
What does it mean that it gives 0? I mean, what you're basically saying is that it's background noise, that
right.
It's spraying itself into the ether, so to speak. That it's not.
What's the symmetrical way of resolving these two lists? And so my claim is that this is exactly the case where the two things are on opposite ends of branch Hill space, and it's also, I think, exactly the case where the only symmetric resolution is to go, blank blank.
But I think it's a different way of thinking about it, which is that what's happening is if you've got this GD6, and they wind up in opposite sides of branch Hill space.
Yep.
But your goal is to make a measurement where something definite will have happened. It's like CDMA telephony, he says rather uselessly.
I have no idea what this is.
Well, I mean, basically what I'm saying is, unless you're projecting in a direction close to the direction the geodesic is going in, the claim would have to be that it's essentially spreading that your measurement device, okay, you could make a quantum observation frame that would measure something going in the direction of a particular geodesic.
Mm-hmm.
But by the time your quantum observation frame is measuring across this whole, across half of branch hill space, so to speak, it's not going to see anything.
Right. It can't distinguish what it sees from just like background.
Yeah, that would be my thought.
Yep. No, I agree. I think that's the right intuition.
But when there are two things that are nearby in phase,
mm-hmm. That means that they don't conflict, or they don't conflict much. Your measurement device can measure, can make consistent measurements of both simultaneously.
Yeah.
Right. That would be like the 1001 case.
Yeah, I agree. By the way, it'd be good to have for these fizzies on whenever it is, Tuesday, Wednesday, I can't remember which day it is.
Mm-hmm.
It will be good to have some. I mean, this proof by compilation, I think, is going to be quite a powerful technique.
Yeah, I agree. I think this is really nice. It's been fun to work on.
Right, but I think in general, proof by compilation, that basically, if you can reproduce black hole mergers with causal graphs and things, then it's like,
the game is up.
Yeah, I think so. I mean, it's kind of like I mean, then you have to say, well, what's underneath the causal graph? What's the low-level machine code underneath the causal graph? But that's a much more detailed question.
Mm-hmm.
And we really should try and get the path integral. We should
really
try and get somebody to work on that, because I don't know what the state of technology is, that I'm 40 years out of date, but I doubt it's advanced very much.
Right. That seems to be a common theme, that fields that you leave end up not advancing very much. I'm not sure whether that's correlatory or causatory.
Yeah, right. I think it's yeah. No, I mean, I'm pretty sure, I have to look it up what lattice gauge theory has done, but I don't think it's done very much. I think the same problems that existed before still exist. Anyway, you should go to sleep, but black hole winds the winds of change are blowing for black holes.
Right.
All right.
Okay.
All right. See you later.
Bye.
Okay, bye.